Hey guys, and welcome to this video. This is the second and last part of the lecture video on the topic of surface integrals of scalar fields. In the first part, we learned the definition of the surface integral of a scalar field and how to evaluate such an integral given a parametrization of the surface. If you have not seen the first video, please see it first. For this part, we evaluate surface integrals over surfaces defined by functions in x and y. Let's start. Suppose we have a function f of x, y, z that is continuous on the smooth surface S defined by the function z equals g of xy, where xy is in some region R. First, recall from the previous video that if S is parameterized by R of uv, where uv is in some region D, then the surface integral of f of xyz d sigma over the surface S can be expressed as a double integral over the region D of your f of xyz is expressed in terms of the parameters u and v, so we have f of r of uv, and d sigma becomes the magnitude of ru uv cross rv uv dA. In our case, a straightforward parameterization of surface S given by z equals g of xy is obtained by taking the parameters to be x and y. That is, we get a parameterization r of xy of surface S with components x, y, and your z, which is now g of xy, where xy is in the region R. Now, what happens to this formula if we use this parameterization of surface S? In the formula, f of r of uv now becomes f of r of xy, which we can simply write as f of xy. And since z is equal to g of xy, we have g of xy. Next, the magnitude of ru uv cross rv uv now becomes the magnitude of rxxy cross ryxy. Keeping in mind that these are the components of r of xy, we obtain that rx has x component 1, has y component 0, and has z component the partial of g with respect to x at xy. Similarly, ry has x component 0, has y component 1, and has z component the partial of g with respect to y at xy. We can now compute for the cross product of rx and ry. Rx cross ry has x component, the negative of the partial of g with respect to x at xy, has y component, the negative of the partial of g with respect to x at xy, and has z component 1. Thus, we obtain the magnitude of rx cross ry to be given by the square root of the square of the partial of g with respect to x at xy plus the square of the partial of g with respect to y at xy plus 1 squared, which is 1. These computations now yield the formula for the surface integral of f of xyz d sigma over the surface S defined by the function z equals g of xy, where xy is in the region R. Therefore, we have the following remark. Suppose S is a surface defined by the function z is equal to g of xy, where xy is in the region R. Furthermore, we assume that g, gx, and gy are all continuous on the region R, and that the function f of xyz is continuous on the surface S. Then, the surface integral of f of xyz d sigma over S can be expressed as a double integral over the region R of f of xyz here becomes f of xy g of xy, and d sigma here becomes the square root of 1 plus the square of gxxy plus the square of gyxy dA. Note that the condition that g, gx, and gy are continuous on R ensures that surface S is smooth. As an exercise, try to come up with formulas for the surface integral of f of xyz d sigma over S if S is instead defined as the function y is equal to g of xz and as the function x is equal to g of yz. If you do the exercise, you will see that you arrive at similar formulas. We continue with some examples that illustrate this remark. For the first example, we are being asked to evaluate the surface integral of f of xyz d sigma over S, where f of xyz is the function 2x minus z, and S is the portion of the plane 2x plus 2y plus z is equal to 4 in the first octant. Before we can start, we need to express S in the form z is equal to g of xy. Since S has equation 2x plus 2y plus z is equal to 4, we can isolate z in this equation to obtain z is equal to g of xy is equal to 4 minus 2x minus 2y. From the previous remark, we are able to write this surface integral as a double integral. We have the double integral over the region R of, here, to obtain f of xy g of xy, we replace z in f of xyz by g of xy. Thus, we get 2x minus z, which is now 4 minus 2x minus 2y. For the next factor, we need the partial derivatives of g with respect to x and with respect to y. Looking at g of xy, we see that both partial derivatives of g with respect to x and with respect to y are equal to negative 2. Continuing, we have the square root of 1 plus the square of gx, which is 4, plus the square of gy, which is also 4, dA. Note that this expression reduces to square root of 9 or 3, which we can factor out of the double integral. We now have 3 times the double integral over the region R of, simplifying the integrand, we get 4x plus 2y minus 4 dA. In order to write this double integral as an iterated integral, we now need to identify region R. Recall that R is the region over which the surface S described by z is equal to g of xy is defined. This means that graphically, region R is the shadow of surface S on the xy plane, or the projection of surface S on the xy plane. If region R is not explicitly stated, which is the case in this example, it is then helpful to sketch surface S to locate region R. Recall that in our example, surface S is the portion of the plane in the first octant with x-intercept 2 obtained by setting y and z to 0, similarly with y-intercept 2 and with z-intercept 4. From these intercepts, it is easy to draw surface S, which we show in red in this figure. We see that projecting the points of surface S on the xy plane below yields this isosceles right triangle, which is then region R. Some students find it useful to draw the region R in a separate xy plane, which we do for this example. The vertices of the isosceles right triangle are the origin, 2, 0, and 0, 2. Thus, we obtain region R. Now, we are ready to finish evaluating the surface integral. We have 3 times the integral of 4x plus 2y minus 4. If we choose to integrate first with respect to the variable x, we get dx, where x starts from here, where x is equal to 0, to the x of the hypotenuse of right triangle R. The hypotenuse of right triangle R is located here in this figure, and this line is exactly the xy trace of the plane with equation 2x plus 2y plus z is equal to 4. Hence, the hypotenuse of right triangle R has equation 2x plus 2y is equal to 4. Simplifying, we have x plus y is equal to 2, and isolating x, we get x is equal to 2 minus y. Thus, the upper limit of integration here should be x is equal to 2 minus 1. Next, we integrate with respect to y. So we get dy, where y starts from here, where y is equal to 0, to y here, where y is equal to 2. We now evaluate this iterated integral. We have 3 times the integral from 0 to 2. Integrating 4x plus 2y minus 4 with respect to x, we get 2x squared plus 2xy minus 4x, evaluated from x is equal to 0 to x is equal to 2 minus y dy. Before we continue further, note that we can factor out x from this expression to obtain x multiplied by the quantity 2x plus 2y minus 4. Continuing, we now have 3 times the integral from 0 to 2. We evaluate this expression at x equals 2 minus y to get 2 minus y multiplied by the quantity 2 times the quantity 2 minus y plus 2y minus 4. Evaluating again this expression at x equals 0, yields 0, so we get here dy. However, if we multiply out 2 here, we obtain 4 minus 2y. And we see that 2y and minus 2y, as well as 4 and minus 4, cancel. And so, we are left with 3 times the integral from 0 to 2 of 0 dy, which means that the value of the surface integral is 0. Consider the portion of the paraboloid with equation z equals x squared plus y squared between the planes z equals 1 and z equals 2. Let us call it surface S. In this example, we are being asked to find the mass of surface S, given that the density at any point xyz on S is f of xyz equals 1 all over the square root of 1 plus 4z. Recall that the mass m of surface S is given by the surface integral of the density function f of xyz d sigma over S. If we wish to use the previous remark To evaluate this surface integral, we need to represent surface S in the form z equals g of xy. Since surface S is part of the paraboloid with equation z equals x squared plus y squared, we clearly have that z is equal to g of xy is equal to x squared plus y squared. The previous remark tells us that the surface integral is equal to the double integral over some region R of, we need to express f of xyz in terms of xy, and so we have 1 all over the square root of 1 plus 4 times z, where z is equal to g of xy equals x squared plus y squared. For the next factor, we need the partial derivatives of g with respect to x and with respect to y. We see from g of xy that the partial derivative of g with respect to x is equal to 2x, and the partial derivative of g with respect to y is equal to 2y. Continuing here, we have times the square root of 1 plus the square of gx, which is 4x squared, plus the square of gy, which is 4y squared, dA. Note that if we multiply out 4 here, we obtain 4x squared plus 4y squared. And we see that these two expressions are equal and they cancel out. Hence, we are left with the double integral of dA over the region R, which is simply the area of region R. Therefore, all that remains is for us to identify region R, and for that, we sketch surface S. The surface S is shown in red on the right. Remember that S is the part of the paraboloid z equals x squared plus y squared between the planes z equals 1 and z equals 2. To find region R on the xy plane, all we need to do is to project the points of surface S onto the xy plane. Observe that the upper boundary of surface S is projected onto a circle on the xy plane. Similarly, the lower boundary of surface S is projected onto a smaller circle on the xy plane. Hence, the projection of surface S onto the xy plane is the region R between the two circles. To determine the equation of the outer circle, note that the upper boundary of surface S is the intersection of the paraboloid z equals x squared plus y squared and the plane z equals 2. Therefore, the equation of the outer circle on the xy plane is obtained by equating the corresponding equations for z, which yields x squared plus y squared is equal to 2. Thus, the outer circle is centered at the origin and radius square root of 2. The equation of the inner circle is determined in a similar manner, and we obtain that the inner circle is the unit circle. That is, the inner circle is centered at the origin and has radius 1. Finally, we get that the area of R is equal to the area of the outer circle minus the area of the inner circle. Thus, the mass of S is given by pi times the square of the outer radius, which is square root of 2, minus pi times the square of the inner radius, which is 1, which simplifies to pi. We now arrive at the end of this lecture video. I hope you realize that evaluating surface integrals of scalar fields can be a bit tedious. That is why it is important that you practice on the following exercises. For part 1, you are asked to evaluate the following surface integrals, while in part 2, you are asked to compute for the mass of the following curved laminas. If you have any questions or suggestions, kindly comment them below. Also, please do not forget to watch the discussion videos for this lecture. Thank you for your attention and goodbye.